All right, now this next topic, which deals with electric field, is something that describes attraction between two charges, or repulsion between two like charges. The video that you should be watching before you do this, it talks about how we have a positive point charge with electric field going toward it. Now, there are no lines that go from one to the other. There is just a representation of the pull or repulsion between two bodies that are charged. So we have to understand that. It's not like magnetism where you can actually use like iron fillings and around a piece of paper with a magnet underneath it, and you can actually see the magnetic field being formed. That's not the case with electric fields. But we can still use it as a representation for what we call a relative comparison. And then there is, of course, the mathematics involved in it beyond that. But an electric field is a vector field. Now we're going to be dealing with vectors again. I know how much you love vectors. In which you have multiple electrical forces exerting charges strongly on nearby surroundings or environments and weaker ones on distant environments. This means that electric forces are inversely related or proportional to the square of the distance to the effective charges, or 1 over d squared. So we have an electric field in which the vector of electric field, we use E for that, and actually you put a little vector above it, like E vector, but I use the subscript vector here, is equal to the force vector that is being created on a particular charge divided by the charge value. Okay, so remember when we talked about charge, we said coulombs is the measure of charges, and one proton and one electron have the equal charge of 1.60 times 10 to the negative 19 coulombs, because there are 62,500, 6.25 times 10 to the 18th electrons in a coulomb. Now, we have to remember also that we've used Coulomb's law to establish that the force that we're talking about here is K Q1 Q2 over d squared. So let's take a quick look at what this is talking about here. So let's back up over here. Here's two examples of electric fields. We have charged metal plates. One is square, one is circular. Now, when we have charged this plate up as a positive charge, in other words, electrons have been removed from it, we show that the electric field is fanning out in perpendicular directions to the sides of the square. And so this is, we have the arrows going away from the positive charge. Over here, we have a negatively charged circle, and each of these arrows that are representing the electric fields, the electric field, singular, is perpendicular to the surface of the circle at each particular point. All right, and notice that the arrows are pointing towards the negative one, so it's away from the positive and toward the negative. Now, so the equation E equals F over Q, and we use tiny q or big Q. It doesn't really matter. It depends upon the context, and we're not far enough into that to really concern ourselves with it. But the label for the electric field is newtons per coulomb. So how many newtons do we have per coulomb of charge? Okay, now, what we're going to do at this point here is I'm going to name this Q as Q positive. It's going to be a positively charged point. And so in using the Coulomb's law, instead of using Q1 and Q2, I'm going to use Q positive and just plain Q. And it can be either one, doesn't make any difference. But notice that the denominator is d squared for both of these. Now, since the force is equal to this, I'm going to plug this in right over here, and that's what I get right there. So this Q positive is the division of this whole monstrosity that we plugged in or substituted for F. When that happens then, The Q positive goes in the denominator of the D squared, cancels out the Q positive in the numerator, and this gives us our equation right here, which I've highlighted in red in the script as the E vector is K, and it's the same K as Coulomb's law, 9.0 times 10 to the 9th Newton meter squared per Coulomb squared. Q, of course, is in coulombs, and D must be expressed in meters. So that means then, as you can see, that the electric field is inversely related. This is proportional, inversely proportional. When I say inversely, it's the reciprocal of D squared here. So it's inversely proportional to the distance between the two charges squared. And then it is also directly proportional to the amount of charge that we have. So they both have to be taken into consideration. And that comes into play in just a little bit. Okay, so here's a couple of examples of odd-shaped objects that are charged. Now, these are conductors, which means that the electrons are on a metal. Now, metals have electrons that are all on the surface. They have the metallic bonds holding them together, but there are these free electrons, usually because of the D or the F electrons of the metal that we have. They're frequently displaced rather easily. And this is why they're such good conductors of electricity in your house, although not in these shapes, I hope. But you can see, or see that by trying to be an artist here, that all these arrows are going away from the structure perpendicular to the curve at any particular point here. And you can see when you get to a really tight-in curve that they get really close together. And that is what we call a concentrated charge. And I'll get back to that after I take a look at this, say, like a pin here, which is metallic. So now I have the arrows going out, and technically they should be going in, but you know, it's the fact that you have these perpendicular positions going away from the electrons that are being there. They are very easily lost, but I should have the other direction. But regardless, you'll notice right up here how intense that is. Now, what's one of the things they tell you not to stand under when a lightning storm occurs? A tree. Why? Why? That's the reason. Because at the top of the tree you have these branches that are way up high, pointing at the sky. They get a buildup of charges. The electric field built up is high here. And with a tree, it's probably be positive, so this is more representative of a tree branch than it is of a needle. So that, I should have said that at the beginning then, right? But that means then that the electric charges in the clouds will be attracted to that, and sure enough, boom! It's going to knock it. And then anybody under the tree is either getting thrown away from the tree or will have branches falling on top. So this is the reason why they say that. Okay? I gave a couple examples, or 3 examples actually, of problems that you're going to be doing using the 2 equations, Coulomb's law and the electric field formula. And I'm going to put a little twist on it from my end on this, as you'll see in just a little bit. The first example deals with, you have electric field. Now, it doesn't say how far away the object is, but they are saying that the distance is going to be changed by doubling, whatever that is. We do have the first electric field value, which is this quantity right here. And they want to know, under these conditions, what is going to be the value of the electric field when this is pulled twice as far away. Now, if you're pulling a charge farther away, remember it's an inverse relationship to the distance squared, which means we know that when you pull it away, the distance gets greater. That means the strength of the electric field is going to get weaker. So let's see how we can calculate that. There's actually 2 ways to do this problem. I've done one in black and one in red. Now, black is the more mathematical approach. Now, what I did to simplify things, because I really hate writing all that garbage down, although I did do it in the script. But in this formula, E equals KQ over D squared, we're dealing with a charge here, or a quantity of charges. We don't know exactly how much there is, but we do know it's not going to change. We also know that K is a constant, 9 times 10 to the 9th meters squared per coulomb squared. That is not going to change. So we have two constants right here that we have to keep putting down. So I decided to multiply K times Q and call that Z. Z? Why not Z? So I multiply those two values, 9 times 10 to the 9th, or 1.60 times 10 to the negative 19, and I get 1.44 times 10 to the negative 9. That is my constant Z that I'm going to use in this black part of the problem. All right? So, we're given here for E1 equals Z over D1 squared, and we said Z is 1.44 times 10 to the negative 9 over D1 squared. And what I'm going to do now is I'm going to rewrite this equation by flip-flopping the numerator and the denominator here. So that gives me D1 squared equals this complex right here. Then, because that's squared, I have to take the square root of this value here, and I get 0.00379 meters. That's the calculated distance for this system. Now, since D2 equals D1, 2D1, I'm going to substitute 2D1 for D2 in the second equation. So the E2 equals Z over D2 squared. So, but D2 squared now is 0.00758 squared. Divide those out, and I get 2.51 times 10 to the negative 5th newtons per coulomb, which is approximately 1/4 of the original electric field, which will make some more sense why it turned out that way when I go back and show you the other way we could have done it, which is the way that I tend to use. You don't have to. I don't care which process you use. But I like to think that I understand how direct relationships and inverse relationships work, particularly when exponents are involved. In this case, this is an inverse relationship with the distance squared. Well, the E2 is equal to Z over D2 squared, but we said that D2 is equal to 2D1. So I replace D2 squared with parentheses, 2D1 close parentheses squared. Multiply that out, and I got Z over 4D1 squared. Now, what I recognize here is that we originally said that E1 was equal to Z over D1 squared, and there that is right there with a 4 in the denominator. So I pulled that out as the fraction of 1/4 times that E1 value shown right there. And the E1 value said was 1 times 10 to the negative 4th newtons per coulomb. So, and we take 1/4 of that, we get 2.50 times 10 to the negative 5th newtons per coulomb. And we got 2.51 over here. They are the same thing, just a little bit of rounding differences between the two. But if you know that you're going to double the distance that is going to be farther away, then you know if you take 2 and flip it to 1/2 and then square it, you get 1/4. You know your answer is going to be 1/4 of the original value. That is the quick way of doing it.